Good afternoon, participants. I think we can start the third and last session of day 4 of ATAL sponsored FDP. I once again welcome Swapnil sir and request him to continue his session and highlight on the application of machine learning implementation in Tarang. After his explanation, I will continue with the topic machine learning in electromagnetics. Over to you, Swapnil sir.
So yes. So now what we'll do is that we will go back to the PowerPoint slides, and there I will briefly introduce some parts that we covered, and after that we will take hands-on sessions for 2 or 3 examples. So those hands-on sessions will give some idea about that how we are going to use the software, how we are going to simulate the results, and what things we can do from that. And apart from that, in the morning session I had discussed that researchers can also use the software because there are facilities that you can integrate the simulation core of this term software with your own code optimization or any other code, and by doing this integration it is possible to do advanced level projects also. So I'll just do the next slides. So we seen some examples of circuit design in the morning, and then we had simulated some I think diode circuits, RL diode and all. But here in RLC circuit, I had demonstrated that we can use a slider for a series resistance. We can change the slider just to demonstrate that how this overdamping, underdamping responses will come. So in the time domain, it will these responses. Okay, So this when the value of resistor is more, you can see this yellow plot, and when the value of resistance is 0, there will be oscillations. So we can see this green part. Similarly, if you observe these things in the frequency domain, we can see that this overshoot is happening at resonant frequency. So we can play with these kind of things and demonstrate the things to the student. After that, this example we tried in the morning. And if high frequency filter design is also possible. So in high frequency applications, we are basically going to measure the S parameters. And in communication systems, So in morning I had demonstrated the amplitude modulation, but here we are doing the same thing, but I added some DC voltage to shift the envelope upside, and the rectifier circuit that we designed, we just kept as a demodulator circuit. So here we can see that how this blue graph, the demodulated signal will look like. So for now, I just use the random values like 1K and 1 micro like that. But we can properly keep. This is the simplest version of the demodulator. But still, we are getting the signal, which is having in the. If you see the frequency domain, so this is the output signal. So we are getting the signal which is again shifted back to the origin, and but there are some high frequency harmonics. So properly choosing these filters, we can remove those things and we can get the exact demodulated signal. So when we are doing this thinking as a perspective of high frequency scenarios, then in case of electronics, student used to ask me the question that we never use 3D softwares. And what is the role of 3D software? So even in my BTech, I didn't use the 3D software. There was only a layout software which was a basic software, but nowadays this technology is evolving, so we can use these 3D softwares at electronics design also, because we are now working on more and more higher frequencies, and when the frequencies are increasing, there are like a lot of issues that are coming, non-ideal effects, and there are again like well-known effect called as skin effect, then proximity effect, that coupling, and all these things are going to happen. So here in the skin effect, if you see the cross section of a conductor and the current flowing on that particular cross section, then that current is almost uniform at lower frequency, but at higher frequency that current is going to saturate at the outer wall. So because of that, we this resistance of this particular conductor is going to increase as the area is reducing. Same effects are there. Proximity effect, when the current are uh, opposite in the direction, then the current will show that attraction behavior over the cross section, and when they are in the same direction they will be repulsive. So here twisted wire cable, we can see that when we increase the frequency, this effect is going to increase. Similarly, the magnetic field coupling and electric field coupling is going to happen when we have two conductors near to it, and that coupling is again depend on the orientation of the cable, then the separation between the two cables, the length of that cable. So we need to like consider all these parameters, and to model this orientation, length, and everything, we need a 3D software. So we'll start with graphic user interface. So again, I will be like entering this. This user ID, password, API key need to be entered only once. Once you enter, that will like be saved here. So you can start the software. Now we do a few experiments with the same dipole antenna that we had earlier. So I'm taking a wire of like same 200 centimeter, because the concepts are going to work. So we can change the frequency, we can change the length, and those things accordingly. Now, okay, I'll make it center and run it. So I will try to run this model for now to 300 megahertz from, let's say, lower frequency, which can be like 5 megahertz. With number of points is I will make it 71, just to fasten the analysis. If we have more number of points, it is going to calculate the response at all the frequencies. So I just reduce the frequency points because I reduced the last frequency from 500 to 300 mega. So we can simulate now. Now here we can see these results. The real part of input impedance. Now it is again close to 1400. Then S parameters. So the S parameter is again showing this dip around 75 megahertz. So the same things we simulated earlier. We can also see, okay, this 3D, what we can say, near fields. Okay, any dimension you can enter. So 1100, anything is fine. So it is basically the area where you want to plot these fields. Just make it minus 2000 to plus 2000. Yes, with all sides are like 51, 51 by 51. Now we will see this radiation pattern also, and this near field cut plane. Okay, I think okay, fine. For now, what we'll do is that we'll play play these animations. So here I wanted to show that the field variation is like circles from the top, yeah, and from the side it is like this donut miss. You can just imagine that the radiation pattern and the near field are little bit similar. Means from the top it is circle, and from side if you see it is like propagating like in this way. And now we will see this imaginary part of input impedance. Yes, so here these two things can be noted. In the imaginary part of input impedance, we have capacitive part. Means this is starting from negative, and then it is becoming zero somewhere here where the resonance is happening, and after that it is positive and again negative and positive. So at initial stage it is capacitive. So that means that this open wire dipole antenna, when we consider open wire, so it will be like capacitor. It will act as a capacitor because this is one wire, and there is like electric field coupling between this two wires. So basically, it is a capacitor. So we can see this is a capacitor, and at DC frequency, this capacitance will have zero value. That means it is like minus infinity. Now what we will try to do is that we will try to add few more wires here to make a loop, closed loop. So we'll take, for now I'm just randomly using 20 value so that width of this loop will be 20. So I will add one more wire here and then two more wires from top and bottom. Okay, from this 0 to 20, X will vary and Z will be fixed. This is the upside and the downside wire. It will be changing 0 to 20, and for here I will make minus minus. Yes, so we can see that the loop is created. There are like 4 wires joined like this. Now we'll run this simulation once again to see what is happening. Yes, so this simulation has performed, and we will like see this real part of input impedance now. Yeah, so if you compare the real part of input impedance here in the both diagrams, so in case of dipole antenna, the real part of input impedance is less as compared to the like input impedance of this folded dipole antenna. So we'll see that why this is more here. And again, if you see this condition, then we can also see that the radiation resistance in case of folded dipole antenna, the R in is greater than radiation resistance, and the value of R in is very much. So because of that, this P in and P rad we can compare them, because P in is directly proportional to square of R in, and P rad is directly proportional to square of R rad. So here, if R in is more than R rad, so P in will be more than P rad. That means whatever power we are feeding is very more than the radiated power. It is as compared to the dipole antenna. That means the efficiency of this particular thing is going to reduce because P rad is less, P in is more. Now we will see this imaginary part. So in the imaginary part, again, if you compare these two plots, so here it was like capacitive, but now this is a shorted cable. So when we have a shorted cable, it is going to behave like an inductor. So here, this case, we call this as a current radiator. The earlier case, we simulated the dipole antenna, that is like voltage radiator. So that voltage radiator means basically the radiation are because of the electric field, and here the radiations are because of the magnetic field. So if you also see these radiation patterns, then also you can got to know these things. So here in the radiation pattern of the loop antenna, the fields, okay, we will simulate the circular loop antenna to know it in better way. So the fields are because of the magnetic field. So we'll also take the case of circular loop antenna, and now we'll see this. Okay, there is this. S parameter. So I'll just close these two. So in the S parameter, here we are getting a dip at 75 megahertz. In this case also we have a dip around 75 megahertz, but this value of dip is very like not less than minus 10 dB. And so we can say that this antenna is not operate, means it is like having the resonance at this frequency, but it is not better to operate this antenna at this frequency because of the mismatch. We are feeding a power, but it is not getting delivered to the antenna, and that mismatch is there. Because of that, we need to like figure out some things here so that this mismatch can be reduced and we will get maximum, like minimum reflection. That means this dip will be more deep. So as we know that there is a impedance mismatch, to match that impedance we need to know that the impedance mismatch is because the port impedance is not equal to the input impedance of the antenna, and when we make these two things equal, then we will have this result, better performance. So to match this impedance, what we can do is that there is like a analytical formula also in the textbook about this n element folded dipole antenna or folded dipole antenna. So the formula is mentioned is that Zn is equal to n square Z0, number of elements square into Z0. So now here number of elements, if you see the current distribution, so we can know that the number of elements are equal to 2 because there are like 2 such peaks. So I also plot in 2D. So okay, this is like very small current. It is along this particular direction. We are not going to focus on this current because this dimension is also very small and this value is also small. So basically these are the two main current elements. So because yeah, this is like half wavelength for one element, second element, this is half wavelength. So because of this reason, we can say that this is a 2-element folded dipole antenna. We can also have multiple element 3, 4, 5. So based on that formula n square z0, that characteristic impedance here we need to take is like 50 into 2 square because of number n is equal to 2. So that will turn out to be 200. So if I choose a 200 port impedance here, then we will get a better match. So we'll check that now. So I'll just make this impedance 200 and we'll see. Yes. Again, we'll plot these as parameters. Now if you compare the earlier, okay, this one is for dipole antenna. I'll close this. This is folded dipole, earlier case where dip was not there in the 10 dip at 7.5 megahertz, 75 megahertz. And this is like the pattern where we are getting a dip. And this dip is like less than minus 10 dB. So now we can say that this antenna is matching at this particular frequency range. So we can operate these antennas at that frequency because we have properly chosen the like impedance and all. And in this way we had like in this case we had done we tried to modify our port impedance so that the impedance will match. So if you see the antennas, the folded simple dipole antenna we used to feed with coaxial line because coaxial line has impedance 73, like 50 ohm only, and antenna has around 73, and it shows a better match. But if we try to feed this folded dipole antenna with coaxial line, it will cause some problem. It will not match. So if you seen that old Yagi antennas and all those antennas, there is like folded dipole antenna element as a driving element, and that element we didn't use to fed with the coaxial line. We used to fed with that parallel cable wire. So we need to like change the wire for feeding that antenna, and that particular wire has that impedance 200 around. So we can make this kind of like arrangement. So in some cases it is also like a requirement that they want to feed with coaxial line only. So in that case they need to modify the Rin. Right now we modified the Z0, but we can also modify Z in to get the better match. And to do that, we can do there are different ways to do that, like the simple that we had learned earlier, RLC loading and all. So we can try those things, or we can try any other things to match that, to get that match. Now we'll take one more example of circular loop antenna. We just so what we will do is that we are going to use the same wire which was having length is equal to 200 centimeter. So if we try to like find out the radius of that wire when we make it as a circular form, so that R will be around 31.83. So I'll directly use this value as 31.83, and the location of this loop is at center 0, 0, 0. So now we will like the same wire we are using, so we will like make this as a radiator with diameter is equal to 1 centimeter, and material is again copper. Now we'll apply the excitation. So okay, that's fine, miss. Even if this excitation is fine, but in case you want to like give a exact location, so you can mention like 31.83. But it is going to calculate the closest point and going to apply the excitation accordingly, and you can make it 0 here. And characteristic impedance, we'll put it 50 only. Here our more interest is to find out the radiation effects and the current distribution. So yeah, now we'll run this simulation at single frequency. Operation frequency I will like reduce for now. I will make it 15 megahertz. Yes. So after simulating this design, we can see this current distribution, and more interest is in radiation pattern. So we can see this radiation pattern. So this radiation pattern is almost same to the radiation pattern of dipole antenna, but there is a difference between these two radiation pattern. In case of dipole antenna, the red part that we were seeing is because of the E theta. E theta component was there, which was getting propagated. Now here the loop is located like horizontal, like this, and these components are H theta, and E will be in the direction of phi. Okay. In earlier case, there was E theta and H was in the direction of phi. So that is the basic difference. So here we can see that these components are rotated. Means there it was like E theta, here it is E phi. And now just imagine that what will happen if we combine the both the things, this circular loop antenna as well as the vertical dipole antenna. So we will get E theta because of that vertical dipole, and we will get E phi because of this loop antenna. Similarly, there we were getting H phi, and here it is H theta. So it is like both the combination of H theta and H phi we will get. That means by combining the two antennas, we can achieve both the components, E theta and E phi. And in case those two components are in out of phase, like 90 degree, so in that case we can get the circular polarization. So the circular polarization means that there are two like electric field components which are orthogonal to each other and shifted by 90 degree. So E theta and if there are E theta and E phi, or Ex and Ey, so and if they are like 90 degree out of phase, then the way it is like going to propagate will be like in a circular fashion it is going to propagate. So that circular polarization we can achieve by combining the two antennas. So okay, right now we don't have a lot of time to discuss that examples and all, but I have also simulated the combination of these loop antenna and dipole antenna. Then we plotted the near field, and we just seen that how it is like propagating in a circular fashion. So we have observed that circular polarization also. And in the same case, now in the folded dipole antenna, we have seen that to increase the impedance, that n square z0 formula we have seen. Even in case of array antennas also we have seen that if we have more number of elements, we are going to increase the directivity. Okay, so I'll like explain that concept just now. So for that, first we'll like do this simulation at higher frequency. We'll see that what is going to happen at higher frequencies with this loop antenna. So I will make this frequency as 75 megahertz, because right now it is omnidirectional pattern. So that directional pattern we will talk once we get the directional pattern here. So okay, so now after increasing the frequency, the thing we can observe here is that this radiation is, this blue spot is saying that these radiations are maximum in this direction. So we can say that the radiation like getting increasing towards this particular direction. So this case doesn't happens with the dipole antenna, but here we are observing this thing. Now once again I will increase the frequency to, let's say, instead of 75 we will go for like 150 megahertz. Now again I will plot the radiation pattern. So now here we can see that the radiation pattern, previously it was like this. Now this radiation was increased towards the axis, and we will get the directional radiation pattern. And we can also imagine that this radiation pattern is getting shifted. Like it was previously like this, and now it is becoming this. Here in the axis direction, the radiation was 0, but in this case, the radiation is maximum towards the axis. So it is the way like this radiation pattern is shifted. Similar shifting and other shifting of radiation pattern is required in antenna design, but we don't do it with this loop antennas. In many cases, we prefer to do those things with the array antennas, the radiation pattern rotations and all, because array antennas are like more convenient, and they are also like by electronically we can control the phase, and we can monitor the radiation, and we can achieve the radiation wherever we want, and we can do the beam scanning and all. So in that cases we use the array antennas, but yeah, but here we can observe the change that we have this radiation pattern at lower frequency, at higher frequency we have this. So this particular radiation pattern is called as normal mode of operation, and here this one is called as axial mode of operation. So these two modes of operation can be observed, and uh, just in case of array, if you want to like increase the length, increase this directivity, we can add more number of elements. So similarly here also we can add more these loop turns, circular turns, to achieve this more directivity in the axis direction. And to achieve this circular polarization, we can also add the dipole. So let's imagine a condition when we have a dipole, vertical dipole, and multiple number of turns. So there will be a wire, and there will be like lot of loops. So that particular design can be approximated or can be equivalent to the helical antenna. So helical antenna is the antenna where we can get better directivity, and because of that we can use that particular antenna as a transmitter also, because earlier we had here we can see that these loop antennas are not good transmitter because of this p rad and p in that comparison we had. So here we don't have, we cannot achieve more p rad, because of that we use these antennas as a sensor. So in biomedical applications, in sensor applications, we mostly see these loop antennas, but in transmission application we don't use these loop antennas. But if we use multiple turns and make an arrangement of like dipole or helical antenna uh, in some other way, then we can achieve more directivity because of this number of turns are increased. The p rad is also going to increase because this impedance is going to increase from the formula of L square Z0. So we can achieve more directivity, plus we can get the benefit of transmission. So we can make a better transmitter when we just modify this design and make a helical kind of structure. And the second benefit of that helical transmitter is that we are getting a circularly polarized signal. So in case of that, means when we have vertical dipole antenna, and at the receiver when we have vertical dipole antenna, then only we will get the signal. But when we have vertical dipole and at receiver we have horizontal dipole, then the received signal will be zero. That polarization mismatch will happen. But when we have a circularly polarized radiator, in that case, whether the receiver is vertical or horizontal, that doesn't matter. So it is going to get the signal. So this is the way that this is the second benefit that we can have with the helical antenna. One is like increased transmission capabilities, and second is the wave is circularly polarized. So at the receiver, it is not necessary to orient the antenna. So we'll like see one example of helical antenna now. Yes. So here we have these helical antennas and the number of turns and everything. So uh, I have few more examples like spiral antenna, just slider, change the slider and change the number of turns and observe the ultra wideband behavior. There are like a lot of examples I'm having, but yeah, we had also prepared the tutorials. I will explain those examples if possible, but I think that may not be possible right now. So for now, I'll just explain this helical antenna. Again, we are going to do the same things. I will like observe this helical antenna at lower frequency. Let's say 50 megahertz. We can also write E6, 50 megahertz. So because of this helical structure is having a lot of elements, it's going to take a little bit more time to get simulation. But yes, even though the software is faster, because the technique we are using, we are not making a volumetric machine here. So that is the reason we will have less number of unknowns and we will get better result in less time. So now here we can see the current distribution. So the current distribution in the lower frequency is more like dipole antenna only. It is like maximum at the center and minimum at the end. But it is like distributed on the, like here we can see minimum at the end, maximum at the center, and it will be like on these helical structures. Okay, and now we will see this after current distribution. We will see the radiation pattern. So the radiation pattern is also like somewhat similar to the helical this dipole antenna only. The same thing we observed in the case of circular loop. Now we will run. I'll just increase the frequency by 10 times. I will just add one more zero here. Now we'll see what is going to happen if I increase the frequency. The same thing we seen in the circular antenna, circular loop, the same thing is going to happen here. The radiation will be maximum along the axis. But here we will have more directivity because of this more number of turns. Yes. So I'll plot these results now. So at higher frequency, we can see this. Okay. I need to plot that current distribution also. Yeah. So here, if you compare these two radiation pattern, this is like axial mode of operation, which is having more directivity now. And why we are getting more directivity, I will explain. So here there is like only one peak at the center, and at the end there is like zero current in case of earlier lower frequency example. Now I'll plot the current distribution. Now I'll just close this old window. Yeah. So here if you see, these currents are repetitive. Here it is like maximum, minimum, again maximum, minimum, maximum, minimum. So I can also draw this in 2D. So these are the like current variations that are, these are like changing very much. Maximas, minimas are there. So this is a basically like somewhat similar to array antenna. In array antenna also that current is like repetitive. So these are the current somewhat repetitive, we can say. There's like the maximum at the center because we are applying excitation here. But the repetitive nature we can see similar to array antennas, and because of that we have this increased directivity. Now I'll go back to the slides. Yeah. Okay. I think there are like many things that because of like short time, those things I might not be able to present right now. But yeah, there are like other many examples we can do and we can simulate. So I'll just explain the benefit. I hope that you might got the in like yesterday's webinar and today's morning webinar. So based on that, you might have got that this platform is going to be very much useful for the student as well as faculties for teaching the like tedious subjects like electromagnetics as well as many other subjects of electronics, plus the most complicated subject that we focus today is antenna design. And you can also read out these things, so like there is like a lot of freedom for the teacher that he can do, add his own things, contents, he can create his own graphic user interface elements, he can be on the portal and interact with the portal, he can share the simulation model. Those simulation model can be opened in their Android smartphones. Student can access those things in their smartphones. They can access on the web portal, they can make the submission, they can perform the simulation, they can make the measurements, and faculty can monitor the performance of the student. There is also facility of automatic sending report cards when student performs better like that. So it is like very much easy to map the program outcome, course outcome, that new strategy is there, objective like CO mapping. So those kind of things also can be achieved. So basic goal is that instead of like just understanding the thing and submitting the answers, here we have one added benefit that student will make the performance like perform the simulations, and after that they will do the simulation that assignments and all. So the basic goal is that students should perform these simulations on the platform, and they should understand the things practically, and in this way they are just sending their performance to the faculty directly. And very recently we had also worked on machine learning algorithm, because in Numerigen we are like developing advanced technologies very much, and like very recently we had these cloud platforms, then many other like portal and these numerical techniques, and we are like technologically we are following all the trends that are happening, because we feel that if we follow these technological trends and give the solutions to the student, even though it is like electronic student, but they will get the idea that what technologies are going to happen, and they can even excel their electronic skill by updating the technological skill. So these are the things, like even these upgradations are there required for mechanical engineering, electronics engineering. So yeah, so because of that reason we also entered into machine learning, and we had performed several practices for machine learning in antenna design, and our paper is under process, so we are like it is getting published in the public, that research paper is in the publication stage. So we had like simulated the results of antenna using Tarang first. The way that like I in the morning I had demonstrated that slider, and the after changing the slider diameter increases, and we can like see the how the plots are changing. So similar idea, we had like done the simulation over the slider, we increased the number of sliders, so there are like something around 100 kind of 100 around 100 results we had obtained. And then we developed a linear regression based machine learning training algorithm. So that algorithm was like understanding those result input impedance, and it was getting trained and evolved by that training algorithms. And here the reason we used input impedance or input resistance and input reactance is that when we know the input resistance or input impedance, we can calculate S parameter, because S parameter is like input impedance minus port impedance divided by input impedance divided by plus port impedance. So from that we can calculate S parameter. Once we get the S parameter, we can calculate VSWR, and we can also draw the Smith chart and all these things. So because of that reason, we considered this input impedance is the basic parameter from where we can derive other parameters. And then we done this training approach for input resistance, but the same thing is like once input resistance is trained, that means automatically the S parameters and VSWR and other parameters are also getting trained. So here in the left side, we can see the results. Actually, the Excel sheet is having like a lot of rows, but I had chosen few rows, and I just keeping here. So we can see this simulated result in the Tarang, and we also made these training algorithms and all that, and we also obtained the results from this training, whatever data we trained from the machine learning, and they are like quite matching. But yeah, uh, the only thing is that if the training data is more, the accuracy will be more. If the training data is less, the accuracy will be less. So, and we are also working that how to achieve more and more accuracy even if the training data is less. So yeah, but we had implemented and we had getting good results. Right now in these columns I didn't included this error and all, but we can also make the difference between these two, and that there is error formula also. We can calculate error if we know the ideal value and the practical value, then we can calculate that also. So yeah, and yeah, so this is like a start of our work in the machine learning. It is on entry stage, and we are I am confident that this machine learning things within 5 to 6 within next 5 to 6 months we will be developing more and more mature training algorithms and in the machine learning. And I also wish that uh, Torse sir should plan one more session on this machine learning things, so that we can present that work, the latest work at that time, because right now we also got several plots, but because of it is publication stage, we didn't I didn't kept in the slides here. But that time I can disclose those things. I can share the more experience on that machine learning part. And fortunately I hope that Torsesser is going to organize this kind of webinar in future, because Torsesser himself is very much interested in machine learning. He already worked on machine learning and applications in electromagnetics, and after my session he will be explaining how he what his own work experience on the machine learning, how he used machine learnings into electromagnetics. And we would like to listen from Processor now on the same topic about machine learning. And so I request Processor to take the control and share your experience on the machine learning things. So thank you.
Thank you, Swapnil sir. Thank you for extending the session and explaining about antenna simulation. It is very good to see that, because at one point you mentioned about the speed of execution and the technology that you are using in the Tarang in order to
Yes, sir.
improve speed of simulation.
Yes, sir.
Because most of the CEM tools what we are using have
Yes, sir.
invariably their own disadvantages, and most of the time the major factor that we see is the computational speed. It is
Yes,
affected,
sir.
yeah, it is affected by the boundary conditions that we define,
Yes,
and
sir.
it is here that you are incorporating uh, techniques in order to improve the computation speed.
Yes, sir. Sir, I just missed three screenshot, because that yesterday's cloud service I had demonstrated. So there, students are accessing those computers from their smartphone and they are running the simulation, and that simulation is also running fast, because the reason is that the calculations are happening on the cloud. Those
Okay.
calculations are not happening on their phone. It is on the cloud. The things are going running on the cloud. So even if they have their own computer with 2 GB ram or 1 GB ram, or even it is a smartphone, it is not going to matter, because the actual calculations are there. They just need a good internet connection, and they can directly simulate the things instantly. They will get the result, because the on the cloud there is very nice computer kept which is solving the problem. They just can access the result and see the result. So they need a device just to see the results and get internet connectivity with the cloud. And right now the internet connectivity is not a big problem. So I
No,
hope
no,
that
not at all.
this is
Yes.
going to be helpful for even
And
if institute doesn't have any infrastructure related to higher configuration of computers, we can provide these services. So thank you.
great, sir. Really. And in fact, this simulation kind of experience always gives, because I remember reading preface in
Yes,
one
sir.
of microwave textbooks, Peter Rizzi. If participants, it is a very popular book by Peter Rizzi on microwave passive devices. He says
Okay.
if microwave and electromagnetics is studied without the simulation softwares, it is incomplete. In fact,
Okay. Yes, sir.
it is
Sir,
incomplete study.
Yes, sir. And sir, means there are two opinions. Some people also says that learning the things only from simulation is not going to give you lot of insight, because simulation is going to do all the things, you are not doing anything. So that is also opinion from other people. But I would like to comment on that also. So once you know, because in the case of simulation, what is happening is that the person who is designing that simulation model is already knowing what he is designing, and once that person is knowing that model and whatever he is designing, and he is also knowing how that get problem is getting solved, then automatically he will get that insight. So while designing, we should be like know, at least know our own design, that what we are designing. And once we have that knowledge, then we can like make these simulation tools as a like best tools to like get the knowledge, because simulation tool is going to give us the result in form of knowledge only. So that simulation is going to help you, it is going to give you some knowledge. But while designing, just don't do a random design, do a proper design. So if you do the proper design by knowing the things, then it is going to be helpful only. Yes, sir. Okay, sir.
Yes. Yes,
Yeah.
sir. You're right. Okay. Now, from my end, participants, I can understand the. Okay. 1 second. I'll just share window. I hope my screen is visible. In fact, this presentation I had given earlier, the work that in collaboration with one industry, which is not into communication field, but into microwave heating. The industry is located in Belgavi, where our institute is, and it is very close to our institute in the industrial area. So the name of the industry is Energy Microwave Systems, and they are into microwave heating equipments. They provide these equipments to various organizations, government organizations, as well as private factories. And the main focus, their focus is on developing industry heating equipments, not microwave ovens, so big ovens for industry applications. Rubber molding is there, or food processing. So they had assigned one small work to us in order to detect the overheating of objects, or you can say the products, and that work we carried out, and I thought of presenting it. I think based on that work we had given a presentation already. So here I will give you a very brief idea. um, I I'll like to focus more in this particular lecture on machine learning into antenna design and electromagnetics, rather than explaining you microwave heating. So I will be very quick during these slides. I'll show you one application which uh, was very motivating for all of us. So I'll not go into these details, because we saw during Ramaswamy sir explained on day 2. He explained what is heating, and there is difference between conventional and microwave heating. So I'll skip these slides. I'll be a little fast during my presentation. The more focus will be on one slide, in which I'll be explaining on each section about machine learning. Sorry. Then what are the building blocks of machine learning? What are the parameters we should see when we want to develop a machine learning system for any optimization, whether it is a antenna design optimization, RF circuit optimization, or the application that we presented here, we worked on here, and that is uh, detecting heating profile of particular material. So advantages of microwave heating are enormous compared to the conventional heating, uh, because we all know microwave heating is always uh, inside the uniform heating happens inside the material. So volumetric heating ability, what we say, is the advantage of microwave heating. And microwave heating uh, offers maximum temperature uh, uniformly distributed, which is clearly visible in these pictures. You can see conventional heating, the heating starts from the outer surface. At the inner surface, or you can say the core of the product, always remains cold because it receives the heat later. And in this process, there is a possibility that the product at the outer surfaces may get damaged. And one more very important point to mention why heating is important. Every industry product that comes out, its quality depends on the heating profile that it has experienced. So how important microwave in industrial applications, this we can understand by looking at the quality of that particular product. So I'll be again very fast here. So the problem that we identified at that point of time was local overheating, or what we call as hotspot. And sometimes this hotspot results into thermal runaway. So, microwave heating, as characterized by electromagnetic field distribution within the microwave cavity, we decided to look at the theoretical system, how it will be. And then we observed that there are temperature profiles recorded, like how in the last slide, Swapnil sir showed you a table. In fact, that table had many readings, but he had shown only few readings. Okay. So more number of readings or more number of recordings we get for any system, there is chance we implement machine learning. So what is machine learning, why it is required, these many these are some basic concepts we will be learning later. This was the structure of microwave heating system shown to us. There was some process control using microcontroller. The core of the heating system was magnetron and an antenna, which was transmitting electromagnetic waves into the applicator, heating applicator. There is a obviously a DC power supply to run the magnetron as well as the process control system. And there was a temperature measurement system. Unless we have a powerful sensor, we in fact we had infrared camera. So initially we had a temperature sensor, and the readings were not sufficient in the form of numeric values, so we decided to go with images. This was the structure, again very similar to the previous diagram, and there is a microwave generator, waveguide, and microwave cavity. I will not go in detail of this because every faculty member who is working in microwave laboratory understands these basic requirements. Of course, we do it with the help of klystron, but in industries, due to the high power, magnetron is used. So this was one example we referred to have a similar understanding of the system. But this is not the industry where we visited. This was referred theoretically from one thesis, and I have given the reference of that. I have written reference one. You can see the reference at the end. This was the system. This is, please, you can note down the company website. You can visit the company website and see their products. This was the particular model for which we developed a machine learning algorithm and implemented it using FPGA system. That part was given to a different team because I'm not good at the processor part or VHDL part. We had given them algorithm and a good efficiency. I don't claim it was 88% as a good efficiency, but at the initial stage, it was good because any machine learning algorithm acts as a child learns, or uh, as a newcomer, we learn some new subject. Like initially, we only uh, take the example of learning language. Initially, we are happy only with the sounds, right? No proper word or no proper uh, term comes out of mouth, but only sounds, right? Those sounds makes us happy. Then words come, and then sentences come, and then bigger paragraphs come, and then over the period of time, the system becomes better and better. So I don't say that one attempt what we made was the best. So there is a scope to improve the system by giving better training and obtaining the better results. So 1.45 kilowatt was the power. This was supplied to IIT Roorkee, this system, by Energy Microwave System for laboratory purpose under some Government of India funded project. And this is used for sintering and heating purpose. This looks front. You can see the front panel of this. This looks small, but the overall size of this microwave chamber is quite big. So bigger products can be kept in order to heat or in order to sometimes melt also, right? This was the overall cross-sectional structure of the system. We had placed thermal camera and there were 12 sources from which heat was generated, of course, using magnetron. And you can see the position of slotted antennas from where electromagnetic energy was transmitted inside the cabin. This tool, a block diagram, shows where you had used MATLAB as well as LabVIEW uh, because we required two different systems in order to capture images and process them and give the feedback. So I'll be a little quick. Okay, this slide I had shown to motivate something to do. If industry is not available, then you can do something in the laboratory itself, because this is exactly the microwave test bench setup what we have in the laboratory. There is a solid state source. Few universities have updated the syllabus and they have introduced gun diode by removing klystron and magnetron. Of course, magnetron was never there. Klystron only was there, reflex klystron. But a few colleges have klystron now. Along with that, there is a gun diode as a source. So gun diode is a solid state source. Then there is a circulator, of course, for avoiding any reflected wave. Directional coupler. We know the directional coupler's main functionality is to uh, provide fraction of the energy or fraction of the microwave energy for measuring the power. So it is connected to the power meter. And there is a waveguide, again another directional coupler to measure the power at the output. And there is match load, of course. Any end of test bench cannot be open, so there is a matched load. And in between, on the waveguide, there is a sample kept, which for the laboratory purpose power, we can't say it is heated, but definitely there can be change in the structure. If we keep, we do the simple experimentation of testing the dielectric constant of various dielectric materials. So that can be also one kind of reading. Ultimately what we want here is image or reading. Only then we can introduce machine learning in this. But remember, if we have a number of readings which we usually ask our students to write in laboratory manual, those many readings are not enough to implement machine learning. Machine learning is too high or too complex to use when we have so small readings. Only by observing or only by plotting the graph we can also get the required result. But if you want to introduce machine learning or deep learning, then definitely we need more and more uh, inputs, or we can say more and more training set. So we had used infrared camera compared to fiber optic sensor, uh, and to highlight that I had shown this slide. Why camera is better than fiber optic sensor, which gives only numeric values. Sensor, fiber optic sensor was giving us only temperature values. Compared to that, camera gave us images, and because of images, because of images, it was possible for us to. One second. Sorry, I antenna optimization is one such field where machine learning or its application is worth using. Why? Because there are heating systems and human expertise does not exist. Like we have seen bigger microwave ovens where material is heated, and expecting a supervisor to supervise each and every product's heating profile from all the angles, all these corners is not possible. Humans are unable to explain their expertise. If at all, there were people like even in the industry where we work, there were supervisors who used to tell us more accurately, and that is actually a bigger help for us to understand how should we train a particular neural network. So there were experts who knew at what point of time with what value of temperature variation there is going to be a hotspots generation in the product, and the product is going to get damaged. So the problem with them was the hotspot generation was not uniform. Solution was changing in time. Heating variety of material was varying. Like the supervisor who was working well with metals was unable to explain his reason with rubber. So solution changes in time. If at all you think that you are designing a particular antenna and you know, yesterday, if you remember, day before yesterday, Ravi Kumar sir mentioned in one of his slides that any simulation tool that we use can give us only the rough estimate about the sizes and dimensions of the antenna. Again, through our expertise, we have to decide what should be the exact dimension of the antenna in order to get the required radiation parameters. So when there is variation in solution, we need to introduce machine learning. So before you take up, any participant who wants to introduce machine learning into their work, uh, see to it that you are really in need of machine learning, and other methods are unable to give you the accurate solution. So finally, when we need to adapt solution in a particular case, we can always introduce machine learning. So when we are talking about learning, we are presenting models from a data of a particular example. So keep in mind that the expertise of one person in one particular domain does not uh, specifies him or her to be expert in all the domains. This is a universal truth. So you have developed a system and you claim that your machine learning system is performing superiorly for that particular data. It is not necessary that it should work well with other set of data. So data is cheap and abundant these days. We have multimedia data abundantly available, images, but it is, I'm not talking about the abundant data in the form of, to give you best four examples is number of tweets if we say text, number of images if we say Facebook, and I don't know, there are so many other websites, Instagram or such websites, videos if you say YouTube, and audio if you say video audio calls or music. So abundant is that. When we say abundant is that, now you can't expect one microwave industry in Belgium giving us images of their products. We can't call it as abundant. Where compare images of Instagram and images of such industries producing uh, products and giving us images from infrared camera, this is nowhere comparison as abundant. But still we keep on growing. Like one of my friends who is working in Bennett University, Delhi, he has a very good habit. Whenever he visits any place, uh, and if the host there offers him lunch or dinner or breakfast, he, before eating, uh, uh, wherever he is, in the restaurant, hotel or canteen or mess, wherever he is, before eating his food, he clicks a photograph of the plate. So I asked him once surprisingly, what are you doing? He said, I'm generating data, nothing else. So where this data will be useful, I don't know, but I keep on doing this without fail. Right from the time I started my career as a data scientist or machine learning enthusiast, I click the image. So there is a possibility that we can generate a good set of data if we make a regular habit of clicking the images or recording the videos as the requirement is. So in communication systems also, you have a lot of simulations done in simulating softwares. You have numeric values, you have images, you have radiation patterns. So all those images, we should have a habit of saving them in proper format and proper folders so that we can make a good and useful approximation of that data and build a model. So machine learning is what then? If you have sufficient data, train the machine and expect it to perform or solve some logical optimization problems when it learns from the given data. So past experiences are very important when we say we are learning. The same slides, when I presented for the first time, I had no experience how I should proceed. But when I'm explaining it today, I feel more confident. And that is again because of the past experience and the inferences that I had drawn from the past presentations. So solving a particular optimization problem or solving a classification problem or uh, there is more than classification. Regression problem is important in antennas because we need to predict dimensions of antenna or radiation patterns of antenna, or sometimes classify the radiation patterns of an antenna. So it is an open-end application. We can decide any application that comes in our mind and think of machine learning. So once again, what is machine learning? Here you can see a big picture with this particular color where artificial intelligence is written. Artificial intelligence is a vast area in which creating intelligent machines that can sense, reason, act, and optimize is a wider objective. Specifically, when we take some part of artificial intelligence, then machine learning becomes subsection or sub part of artificial intelligence, where we develop again systems which learn from data, predict without being explicitly programmed. And when we talk about deep learning, which is now becoming very popular, it's again subsection of machine learning and artificial intelligence, where we learn by or we develop systems which learn by underlying features in data using deep neural networks. So features are images in deep neural networks. So when you have image processing in mind, you can always think of deep learning. So these are three broad categories. All of you are aware. This much of basic is nowadays explained to any academician or any person into engineering, that there are three categories in which supervised, unsupervised, or reinforcement learning is possible. Mostly we use supervised and unsupervised at the initial stages, where we have training data, and after training we expect some output which has to be in line with what we have trained. Like say if we have trained the machine to detect heating profile, then it should identify heating profile, not some other parameter like size or thickness or dimensions. Unsupervised learning, we do not provide any training, but over the period, like there are people who learn things in their life without even formal schooling. So they are called unsupervised learning. They learn on their own, but there is no one to supervise them. Reinforcement learning is something which has come now and which is becoming more popular into AI, because when system learns, it gets reward in terms of the learning that has happened. So yeah, this is the slide on which I want to focus more. And I would like to conclude early today because, as I'm mentioning from morning, that I should really appreciate participants who are enthusiastically attending this session from morning on uh, a specific holiday, right? We had no idea when we selected this slot that there is going to be a 14th January and holiday. and how it's going to affect. But I can see many participants enthusiastically attending this from morning. So I'll just focus on these this slide in these modules or these sections, you can say, and then conclude my talk. So as Swapnil sir rightly pointed out, that he is trying, his continuous effort is to make the system faster, because uh, most of you who are working with the computational electromagnetic tools, whether it is based on MOM or uh, the FDTD technique, computational time or computational efficiency, what we say, is a major issue. And that is affected by, most of the time, the boundary condition that we define. And changing these boundary conditions for a specific application is very tough job, because the boundary conditions are defined for specific purpose. So when we are not ready to compromise on boundary condition, there is a possibility that we have to compromise on the accuracy or the computation time. For sometimes, for higher order boundary conditions that we define, the time and memory resources needed are high. This happens in machine learning also. It is now becoming very difficult for researchers to rely on the usual machines which we use, which have maximum of 8 GB of RAM or 1 or 2 GB of graphic card. Okay, we understand that when our data set increases, the computation time goes beyond our patience, and the learning results are also very poor. So time and memory resources need to be restructured, and we require larger systems. Then there are few researchers who come up with some sort of solutions, writing proposals, getting higher order machines, higher end machines, getting GPUs, or using systems which can run faster. For instance, if you have a perfectly uh, optimized machine, then CPU and computational time, in terms of computational domain, we can always achieve better on this side. But we can't always guarantee that all the electromagnetic required results are there, those are achieved. For example, if you are using FDTD, which employs uh, two different time step increments, right? Sometimes there is a need of strong electric field calculation or computation, which largely affected by the stability of the system that we are using. Okay, in that case, what happens? The FDTD won't result into the required analysis results. So we have to compromise on accuracy, or assume that there is a reduced CPU time, because of which this kind of results are obtained. So you take any method, FDTD, MOM, FEM, right, on any design of any antenna, whether it is Yagi, horn, or patch antenna. In that case, the CPU requirement, time requirement, is largely affected with the tools that we are using. And that is where there is a machine learning coming into picture, and its application to optimize the performance of these tools. In comparison to any standard computational electromagnetic tool that we are using, there is a possibility that if we attach ANN, you can see section 4 in this slide, right? I already explained you what is machine learning, what is supervised and unsupervised reinforcement. Machine learning framework also I gave you, right? Application also we discussed. So now, how do we build regressive models, or classification models also, we can say, right? I don't go with all the methods here, but third and fourth one is something which is first one, of course, basic, very basic, and we must learn, or we must start with linear regression, right? Linear regression is something which needs no explanation, because in any ML framework, linear regression comes first, and under supervised category, whenever we have data and we want to predict some real valued solutions or real valued labels for some unseen data, we introduce regression. Regression algorithms include linear regression as mentioned in this slide. Okay. Then there is a possibility that we can go with the kernel modification. We introduce support vector regression, right? Or uh, support vector machines, right? If not support vector regression, we go with support vector machines. So that takes the advantage of least square method as well as support vector classification. If classification is the goal, then we have to label the data from whatever set of data available, then go with either binary classification or non-binary classification. Have 0 1 or have 0 to 1, any value between 0 to 1. But support vector machine or support vector regression is one such tool which has been mostly ignored by uh, researchers after the deep learning or deep neural network came. So there is a major comparison between 3 and 4. We don't go with linear regression or lasso or GPR or uh, the cringing regression actually not required at this point of time because it is more advanced compared to the Gaussian process regression only. So the main focus between third and fourth algorithm, artificial neural network and support vector machine. Right. Support vector machine is the most ignored, as I said once again, it's the most ignored area of machine learning. And when we compare it with the most popular one, neural network, which is deep neural network, it has very wide and very popular applications in classification. And the classification of a support vector machine is inspired by planes, right? Which clearly categorize the data based on the hypothesis defined. So we have a reference plane defined based on the kernel function that is included, and we get a very clear picture of classification using support vector machines. Compared to that, ANN is popular because of the functions available in ANN. Right. So let me tell you what ANN is first, not with the help of this slide. This is very basic one. It goes with how human brain works. It's approximate or appropriate model or simulation of nervous system. All these are uh, things which are compared with the neural networks. Although we say it is not true, right? We say neural network is derived from human brain, but human brain is more complex and more advanced compared to what neural networks we can define. So this is only to make a loose comparison. That's why very loosely we say that it is human brain how works. The human brain has emotions, and bringing those parameters with the help of functions or weights or bias is still a big challenge. So this is one simple structure of neural network where x1, x2 are inputs, 1 and 2 are weights, zero 0.5 is the bias, and y is the output. We can increase number of inputs from 1 to 10. We can increase weights. We can increase the threshold. We can increase the threshold bias. And now, to train this neural network, we need some kind of algorithm. Because without a proper algorithm, there is possibility that the neural network may work like a linear function. Yeah, very important point to mention. I said it will work like a linear function. That means it is not a linear function. It is a non-linear function or non-linear mapping. So, so to train the neural network, we need algorithm called as backpropagation. And that's why I have written here in the bracket, it requires a very deep understanding of what backpropagation algorithm is. So here in this slide, I have tried to demonstrate it with the help of this animation. What is happening now, if you observe the animation 2-3 times, and there's one more advantage of neural networks which is not technologically correct to mention, that the resource available for learning neural network is vast. There are textbooks, notes, courses, um, or you can say blogs, and more importantly, the site which you see in this slide, medium.com or dataanalytics.com or analyticsvidya.com, these sites are well moderated, and whichever articles are written in these sites are well moderated, well understood, well thoroughly examined, and then they are published. So you can see now, I think in 10-15 cycles you have learned how this exactly system is working. So there are some parameters defined. You can see at the very beginning, initial parameter is highlighted. With those initial parameters, each node's information is updated. Okay, and for updating purpose, what is being used? Weights and biases. Weights and biases are initial values which are initialized. When, as and when the parameters are updated and they are propagating in forward direction, at the same time, what loss function is generating, or what loss function is creating, it is creating, or it is instead of saying creating, you can say it is generating the loss between actual value and obtained value, and it is propagating it back. So you can see the forward propagation and backward propagation. At a given point of time, is only forward propagation highlighted or backward propagation highlighted. See, now there is a forward propagation, right? Loss function computes. Now it is backward propagation, and this process continues till we reach the required result. There are so many functions available: stochastic gradient descent, momentum, NAG, ADA ADA delta, RMS prop. Okay, all these, it's not necessary to mention at this point of time. You can experience one or two, like momentum method or stochastic gradient, that is the one basic one. Every method has its own advantage and disadvantage, but remember the target is same, to bring the error to zero. See, every method is now trying to bring the result, final result value to zero, right? So this is one animation I took from Medium website again. Okay, as I said, I'll not extend this till uh, beyond the time, right? That's why I would like to introduce quickly to deep learning. I'll see if there is any message in the chat box. Okay. Yes, sure. I will share these PPTs. Fine. Is now. Organizer, I need to share this link for your attendance and conclude this session, right, by taking you quickly through the deep learning. Deep learning was used, of course, because of images, right, and show you what are the experimental results we have done. Yeah, this was the experimental setup. You can see on the left hand side the actual uh, oven in which there was a product kept which was moving, right? We did two-step verification. In step one, we studied the heating from single feeding source. In step two, we found the heating pattern from multiple feeding sources. So results were obtained and plotted using simple Excel graphs, and these plots were for various temperature variations. We used three algorithms, right? Back propagation was the major one, and based on this, one block diagram was proposed in order to incorporate this system into their existing processor. So directly coming to the future scope, here it's possible if more industries give more data, and that enables us to use deep learning. We can always do a optimization of software and hardware. Yesterday you saw MRI system was purely hardware system. right? So not only in the algorithms that we write, but also in the hardware we can bring in the optimization. Now, quick look at uh, how machine learning can be used in the antenna design optimization. So, when we design an antenna, we look at its frequency, gain, VSWR, all these designs parameters. Initially, we design one using simulation tool, and we know that even after we do EM analysis, those are not the best results we obtain. So, to optimize it and get the final design, we can always introduce the machine learning. So, I'll show you one difference between conventional method and neural network method. This is local optimization used. If you are not using the requirements or required designs, you can always go back and run the full simulation in the EM tool once again, or else you can do machine learning. You have not obtained the required results through the running of EM software, then you can always use global or local optimization techniques using neural networks or support vector machines. This was one paper I referred, machine learning based antenna design for physical layer security in ambient backscatter communication, where there was a tremendous improvement in the results in gain, side lobe level before and after optimization using machine learning. Okay, I would like to conclude this session. We worked on heating system. That was not full-fledged work, I say. Okay, initial only 88% of efficiency, as I mentioned, we have obtained. We are still working on it. Now there is a requirement of images, more and more number of images, because we started getting similar type of images, similar type of training data. So we observed that now we have saturated there, right? Uh, it is not that as a child we always play in our living room. A small kid which is very enthusiastic to learn cricket, right? It takes initially a small bat and starts playing in the living room, and then it comes out and plays in front of the house, and then slowly goes out in a small ground and then goes in a bigger ground. So boundaries just go on expanding unknowingly. So in every aspect, the the work domain or the work area should go on extending unknowingly. Only then it is possible to uh, expand the work. So we have always a scope. If we get more and more data and more uh, training sets, we can bring in a very optimized tool, and we can do it with antennas. With Swapnil sir mentioning about the machine learning into antenna, we can definitely bring in, because our data is available. What we did at that point of time, because my PhD work was on machine learning, we looked at a local problem which was readily available with us. They said, we have this issue, can we provide us a solution? We said we can do it with machine learning, and we did it. But we understood that the number of data samples required are now saturating. So we thought of now bringing in machine learning into antenna design concepts. Okay, so we can always use a better and better software. So instead of C, we have moved to Python. Python 2, we can think of Julia, R. All these tools can give us better results in terms of speed of computation and the accuracy of results. So an optimization of antenna is with more faster results on larger data set is also possible. So these were some papers we referred specifically to mention the adaptive and intelligent temperature control of microwave heating system with multiple sources. This was our uh, a pilot project, like what is available existing that we did on a newer system, newer data, and we experienced some changes. Thank you. You can contact me. You have my email ID and all other details, phone number, so you can contact me. If you have any specific questions, you can ask. Otherwise, we'll conclude today's session. You can please unmute and ask, or type in the chat box. Swapnil sir?
Yes, it's been nice presentation.
Session, sir.
And yes, sir.
Can we conclude the session, today's
Yes,
session?
sir, sure, sir. And
Yes.
you mentioned that machine learning is very much applicable in antenna designs, and that will be the advanced solutions that we can develop. So, yeah,
Yes,
surely
sir.
we shall look forward for like machine learning in different approaches in electromagnetics, and which is like a combination of computer knowledge as well as the combination of electromagnetic knowledge. Because students are most of the time think that this computer field is like going to be very much useful for them, and they are like most of the time they are confused that electromagnetic things are where shall they apply it, and means
Exactly.
they prefer computer science things rather than electromagnetic things. But if we have this kind of projects, then both the things are clear for the student. They also will get automatically they will get knowledge of computer science and advanced technology, plus they will also get clear knowledge of electromagnetic things, so that combination will
Yes.
be very much helpful for students also. So yeah, thank you, sir.
Okay, sir. Thank you, participants.
So tomorrow at what time test will be there?
Sorry, I was removed from the meeting. I don't know. Being host, I'll stop the recording.